In the next few videos, we're going to begin to talk about some of the topics that I think really attract people into set theory, such as talking about the different sizes of infinity, measuring the sizes of sets, talking about cardinal numbers, and I'm going to start this discussion by talking about the idea of equinumerosity between sets. Up until this point, we've sort of thought about the sizes of sets in a very informal way. That is, we would see some set like A, which has 0, 1, and 2 in it, and say, okay, yeah, this set has 3 members in it. And what we need to start to be able to do is make this process rigorous and spell out what we mean when we say that we're counting the members of a set. For example, what does it correspond to in a symbolic fashion when I say that the set has 3 members, or I'm doing this process of counting the 3 members of the set? So what we really want to do is take some set A and associate some number to it, describing its size. In this case, I very quickly associate the number 3 with the set A. So that's eventually going to lead us into the topic of cardinal numbers. But what I'd like to do in this video is introduce the idea of when we can know that 2 sets have the same size. That is, we're not going to count sets yet. We're not going to associate numbers of a set to a set yet. What we're going to do is set up a procedure by which we can know when 2 sets have the same size. Now, to get us thinking about a good definition for what it means to have for two sets to have the same size, let's count the set, but do a little phenomenological investigation here. Let's sort of investigate what we're thinking about when we're counting this set. So at least for me, when I count the set, I have the number 1 in mind, and I associate that with this element here, 0. And the next, I have the number 2, and I associate that with this element here, 1. And I have the number 3, and I associate that with 2. And then since I've associated all those numbers, 1, 2, 3, with each member of A, 0, 1, and 2, I sort of say in my head, okay, this set has 3 elements in it. And also notice that it didn't matter what order I counted this thing in. I could have counted 2, 0, 1, just as long as I counted every member of the set, and I counted it only once. And those 2 observations, that I counted each member and I counted each member only once, maybe you can pause the video and sort of think about what a good definition would be to say that 2 sets might be the same size in terms of setting up associations between 2 sets. And now let me present the canonical definition of what equinumerosity means between 2 sets. So we're going to say that 2 sets, A and B, are going to be equinumerous, that is, they have the same number, equinumerous, if and only if there exists a bijective function, let's call it h, which maps A onto B. And hopefully you can sort of think about why we want this function to be bijective, that is, injective, or one-to-one, and also surjective, or onto. Now, just to remind you of what this sort of thing looks like, let's say I want to associate the 3 members of F with the 3 members of G, here, here, and here. So we want this function to be surjective because I want all of the members of G to be covered by some input from F. In terms of arrows, what that means is that each point, here, here, and here, is going to have some arrow going to it. For example, I look at E, I see there's some arrow going to E. For G, there's an arrow going there, and F, there's an arrow going there. And I also want this function to be injective, or one-to-one, because I don't want to essentially double count the members here, here, and here. In terms of arrows, what that means is that there's only 1 arrow going to each of these 3 points here. And we're going to say if you can create some bijective function h between A and B, then F and G, in this case, are going to be equinumerous. Now, the advantage of talking about functions only is that we don't actually have to know how many members each set has. We can say that whatever that number is, it's the same number between the 2 sets. So in this video, we're just going to talk about 2 sets, let's say F and G, as being equinumerous. And we're not yet going to associate a number to these sets. And as I suggest, the value of taking this approach is that all talk of the size of sets for now is going to be reduced to talking about functions between sets, namely bijective functions between sets. And from now on, when I say that 2 sets are equinumerous, I'm going to denote that by the wavy equal sign here. So you read this as A is equinumerous to A. Now, one nice thing about equinumerosity is that it has the three features that are reminiscent of an equivalence relation. That is, it has the reflexive, symmetric, and transitive properties. So, for example, for any set A is equinumerous to A. For any two sets A and B, if A is equinumerous to B, then B is also equinumerous to A. And for any three sets, A, B, and C, if A is equinumerous to B, and if B is equinumerous to C, then A is equinumerous to C. And now when you look at all these three properties, the way you'd prove these, which I'm going to do now, is you're going to basically work with bijective functions. So this is the nice thing about equinumerosity, is that you can just prove all these properties by talking about the properties of a bijective function. Now to prove this first reflexive property, I just make the observation that the identity function, I, which maps A onto A, and remember the identity function is going to map any element, in this case A, just back onto itself. And hopefully you've seen from previous videos that the identity function is indeed bijective. So since I found a bijection from A to A is going to be equinumerous to A. All right, that wraps up the reflexive property. So now I'm going to prove the symmetric property. A being equinumerous to B implies that B is equinumerous to A. So by assumption, A is equinumerous to B implies that there's some bijection F, A onto B. And now I just analyze the properties of a bijective function. Since F is bijective, it has a left and right inverse. Now, if you're confused by that statement, the left and right inverses, I would recommend either looking that up yourself or check out my functions video. I think that was part 5. So F is a bijection, which means it has both a left and right inverse, and those inverses are the same function, which I'm going to call F minus 1. Now, F minus 1 is going to be a function from B onto A. And as I said, it serves as a left and right inverse for F. So what that means is that if I compose F minus 1 with F, now F minus 1 in this case is acting as a right inverse for F. That's the same as composing F with F minus 1. In this statement, F minus 1 is serving as a left inverse. These two are both equal to the identity function. Now, if you reinterpret these two statements, if you look at it from the perspective of F minus 1, F is serving as a left inverse. And over here, F is serving as a right inverse for F minus 1. So this also means that F minus 1 has left and right inverses, namely F. So that means that F minus 1 is also a bijection from B onto A. So that proves that B is equinumerous to A, because I just found a bijection. And the third property, the transitive property, I'll just sketch out the proof and you can finish it as an exercise. So by assumption, if A is equinumerous to B and if B is equinumerous to C, then it means there's a bijection F, A onto B, and also a bijection G from B onto C. And now to sketch out the proof, you're going to just analyze this function composition G of F. So we know that the function composition G of F is going to map A onto C. And what you need to show is that G of F is a bijection. Just analyze or come up with what the left and right inverse is for G of F. At this point, I'd like to give you the first application of equinumerosity for infinite sets. Now, what I'm going to do is consider two sets. First, omega, the set of natural numbers, 0, 1, 2, 3, and so on. And now, omega times omega, the Cartesian product, which is going to consist of ordered pairs. For example, 0, 0, 0, 1, 0, 2, and then next you see 0, 3, 0, 4, and so on. And then you pick your next x value, let's say 1, 0, then you have 1, 1, 1, 2, 1, 3, and so on. Then you pick your next x value, 2, 0, 2, 1, 2, 2, and so on, then 3, 0, 3, 1, and so on. And now what we're going to see is that these two sets, omega and omega times omega, are actually equinumerous. Now, it seems a bit counterintuitive because omega times omega, at least to me, it certainly seems to be larger than omega for the reason that you hold one x value constant, and then you've got to range over all the y values to infinity. And then you've got to come back, you've got to select your new x value, let's say 1, then you've got to range over all the y values to infinity, then you've got to pick another x value, and then you've got to range over the x values to infinity. So it certainly seems that omega times omega has got to be larger than omega. But at this point, let me hit you with your first counterintuitive theorem, which is that omega times omega is equinumerous to omega. So if we're going to be able to demonstrate this, we have to find a bijection, let's call it F, which maps omega times omega to omega. That is, for each element in omega times omega, for each one of those ordered pairs, I like to associate it to some natural number in omega. And now it seems extremely counterintuitive, mostly because I've written out omega times omega in this fashion. So when I count this, I'm essentially counting it like this: 0, 1, 2, then the 3, 4, 5, 6, and then I've got to go all the way out to infinity, or so it seems. And then I've got to come all the way back to start at 1, 0, 1, 1, 1, 2, and so on. But let's consider the following counting scheme. So let each one of these points here just denote your usual Cartesian plane. For example, this location here is going to be the origin, 0, 0. Right here is going to be 1, 0, 2, 0, 3, 0, and so on. And then here is like your y-axis here. So this is going to be a point 0, 1, 0, 2, 0, 3. So then I have like a 1, 1, 2, 1 there. And now consider the following counting scheme. So let's say I say that the origin is 0, and then I go up here, and I say this is 1, and then I come diagonally down here to 2, and then instead of going over here, I go up here to 3, and I count down the diagonal 4, 5, and then I repeat that. I go up again to the next position on the y-axis. I count that as 6, 7, 8, 9, and hopefully you can see where this is going. That I'm going to, by this counting scheme, cover all of omega times omega. So let's do precisely that. Let's find this bijection F between omega times omega and omega. So first I'd like to make an observation about these numbers on the y-axis here. The 0, 1, 3, 6, and then 10 would be next. So what I'm going to do is observe that these numbers on the y-axis are the sum of n natural numbers for some value of n. That is, all of these numbers can represent in the fashion 0, 0 plus 1, or 1, and then 0 plus 1 plus 2, which is 3, and then 0 plus 1 plus 2 plus 3 plus 4, which is 6, and then 0 plus 1 plus 2 plus 3 plus 4 plus 5, which is going to be 10 up there. So these numbers on the y-axis are not arbitrary. They're the sum of n natural numbers for some value of n. And then what I'm going to do is I'm going to think of counting some arbitrary ordered pair in the following way. I'm going to look at it. Let's say I take this ordered pair 2, 1 here. I'm going to trace it back up to the y-axis. I'm going to start at that value, which remember can be associated with the sum of n natural numbers. I'm going to start there, and then to reach 2, 1, I'm just going to start there. I'm going to count down 1, 2. So I'm going to count down from the diagonal whatever the x-coordinate of that number was. For example, when I consider 2, 1, I consider its associated number on the y-axis and then count down 2 units. And then if I were over here at the point 3, 0, I would again trace up here. I get to the number 6 and I count down 3 units. So what I have to do is for any arbitrary coordinate, a and ab, I'm going to have to find an expression for the associated number on the y-axis, and to that just add the x-coordinate, or a. And it turns out if you just do your basic equation for a line, if I start at some coordinate here, ab, each of these tracings back up to the y-axis has a slope of -1, and it turns out that the y-intercept is going to be given by a plus b. For example, the point 2, 1, the sum of 2 and 1 is 3, so the y-intercept is going to be 3. And let's say I take the point 3, 0, 3 plus 0 is 3, so the y-intercept is also going to be 3 for that one. So the y-intercept is going to be a plus b, and then I'm going to calculate the sum of a plus b natural numbers. And it has a very well-known formula. Remember, the sum of n natural numbers is n times n plus 1 divided by 2. So what I'm going to do, I'm going to say that f of some order pair ab is going to be equal to the sum of a plus b natural numbers plus a, plus that x-coordinate. And hopefully that makes sense so far. So when I evaluate s or the sum of a plus b natural numbers, I just substitute that right into the formula. So I get the product of a plus b and a plus b plus 1 divided by 2 plus a. And it turns out that this function f is indeed a bijection between omega times omega and omega. And as an exercise, I encourage you to work through the symbols to show that this function f is indeed a bijection between omega times omega and omega. That is, that if I give you any arbitrary natural number, you can find me the ordered pair omega times omega that corresponds to it, and each natural number is only mapped to one time. That is, it's 1 to 1. So I encourage you to go through that as an exercise. Now let me hit you with your second counterintuitive theorem, which is that omega, the set of natural numbers, is equinumerous to the set of integers. Now again, it certainly seems that there ought to be more integers than there are natural numbers, for the following reason: that you can write down the set of integers placing 0 at the center, and then for each of the magnitudes, like 1, there's always a corresponding negative 1. And for 2, you have the corresponding -2. So it certainly seems that in an informal sense, there are twice as many integers as there are natural numbers. And again, it certainly seems like this should be true because I wrote it in this fashion. But let me write the set of integers in a different way. Let me start with 0, and then I group the two integers with magnitude 1 together. Let me write it as -1, 1. And then I group the two integers with magnitude of 2 together. So I'm going to write -2, 2. Then hopefully you can see the pattern: -3, 3, -4, 4, -5, 5, and so on. And then what I'd like to do is map each of these integers to a corresponding natural number. So you can sort of see I can do that already. I can map 0 to 0, 1 to -1, 2 to 1. Then I go 3 to -2, 4 to 2, 5 to -3, and so on. And you can see that such a function, if I can write it down symbolically, should be surjective and injective, meaning that for any integer I give you, you can give me the corresponding natural number, and each of these integers gets counted only once. So I claim that when you think of the set of integers in the second manner, when I write it out like this claim that omega is equinumerous to z is more plausible. Now let me actually go through the proof of that statement, that omega and z are equinumerous. So what I've got to do again is write down a bijection, let's call f, mapping omega onto the integers, or omega onto omega times omega modulo tilde, where tilde is this equivalence relation that two order pairs a and b and c and d are going to be equivalent if a plus d is equal to b plus c. And again, I encourage you to review some of my earlier videos if this seems confusing. So what I'm going to do to set up this bijection f is I'm going to let x be some natural number in omega. Now if x is even, if it's an even number, so it's 0, 2, 4, 6, or so on, I'm going to map it to the equivalence class, again, modulo tilde, of the ordered pair x divided by 2, 0. And hopefully this makes sense if you look at what's going on up here. So if I take the number 6, for example, that's going to get mapped to 3. And what's the integer representation for 3? It's the equivalence class of 6 divided by 2, 0. So it's going to be the equivalence class of 3, 0. And when I map 8 to something in the integers, that's going to get mapped to the equivalence class of 8 over 2 divided by 0, or 4, 0. Now in the other case, when x is odd, we're going to map to something a little bit different. I'm going to map to the equivalence class of 0, x plus 1 over 2. And again, hopefully you can see why this works. If I pick, let's say, 5, I want to map that to -3. So I'm going to add 1 to 5. That's going to give me 6 divided by 2. That gives me 3. But since I want the negative, I'm going to stick that stuff in the second component instead of the first, because I want the negative over here. And again, hopefully you can convince yourself that this is going to map all the odd integers to the, all the odd natural numbers to the appropriate integer. And again, I leave this to use an exercise to work through the symbols and show that this is indeed a bijection between the set of natural numbers and the integers. Now I'd like to introduce a third theorem, but I'm not going to prove it in this video. I'd like to return to this just to prevent loss of rigor when we're talking about this stuff. And the claim is that the set of natural numbers, omega, is equinumerous to the set of rational numbers, q. Now this is the one I think that should be the most counterintuitive, for the reason that when you examine the structure of the rational numbers, they're dense in the rational numbers. There's seemingly a continuum of rational numbers between any 2 points on the number line. So it really shouldn't be the case, seemingly so, it shouldn't be the case that there are as many natural numbers as there are rational numbers. Now, just to introduce you to this claim, remember that the set of rational numbers is z times z prime, where z prime is all the integers excluding 0, modulo tilde, where tilde is that equivalence relation between AB and CD if and only if A times D is equal to B times C. And now I'm going to essentially count the rational numbers in the following manner. I'm going to write the numerator in the same way that I wrote the integers. I'm going to write it as 1, minus 1, 2, minus 2, 3, minus 3, and so on. And then as I go down the columns, I'm going to range over the natural numbers, excluding 0, of course. So I'm going to write it as 1, 2, 3, 4, 5, 6, and so on. And hopefully you can see that any rational number is going to be somewhere on this table. And now I'm going to count it in the following scheme. I'm going to start with 0. I'm going to give that mapping to 0. Or I'm going to map 0 to the rational number 0. I'm going to count over here, first to 1, 1. That's going to get the value 1, then 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and so on. I'm going to sort of weave my way through the table in that manner. And notice that I have to do this in this snake-like pattern, because if I count just across a row, if I start here, I say 0, 1, 2, 3, 4, 5, 6, 7, and so on, I'm never going to actually finish any of the rows. So when I establish this bijection, I essentially have to capture this snake-like pattern that I'm weaving through the table here. And now I'd actually like to write out what that bijection is for you, just to prove that you can actually set up a bijection between these two sets. But if you look closely at what's going on here, is if I just count like this, we're going to lose the injective property very quickly, because we're going to end up double counting the same representation for a rational number. That is, when I count 1/2, 1 over 2, for example, I want to count that only once, and I don't want to count 2, 4 again, because 2, 4, and 1/2 are going to be said to be the same rational number, so I want to count that thing only once. So to preserve that injective property, I'd like to sort of defer this proof to another video. And besides this proof, I'd like to also defer some of the proofs involving the real numbers to another video. I'm sure a lot of you have heard of Cantor's diagonalization argument, where you essentially show that the set of natural numbers is not equinumerous to the set of real numbers. And you do that by considering infinite decimals, at least the informal version is doing that. And I'd like to eventually come back to that, because I'd like to set up a few more concepts before I do that. I'd like to now present one of the more famous theorems in this topic of counting sets and equinumerosity, which is Cantor's theorem. And it's going to say that no set A is equinumerous to its power set P of A. And hopefully this claim is pretty plausible, at least for finite sets. For example, if I have some finite set A, it has n members, then its power set is going to have 2 to the n members. So its power set ought to be larger than that original set. And the proof of this theorem is actually quite simple, but it's worth going through and sort of understanding why it works. So it's going to be a proof by contradiction. Let's suppose that there is some bijection F, which maps A onto the power set of A. Now what I'm going to do is I'm going to construct some special subset of A, which I'm going to call B. That is, if it's a subset of A, it's also a member of the power set of A. And I'm going to claim that this special set is not, it can't possibly be in the range of F. And if I can construct such a set, that'll show that F is not surjective, meaning that I can find something in the power set of A that doesn't get mapped to by some element in A. And I'm going to construct that set B in the following manner. B is going to consist of all the objects X, such that X is both in A, and X has this weird property that X is not a member of F of X. And this predicate here is going to be the key property that allows us to prove the theorem. Now clearly, B is a subset of A because all the members of B are also in A, and therefore B is going to be a member of the power set of A. And now I'm going to show that B can't be in the range of F. And the way I'm going to show that is I'm going to consider for any X value coming from the set A, there is no value F of X that is equal to set B, meaning that there is no F of something that equals the set B. And remember what it means for two sets to be equal. For any member of one set, I should be able to find that in another set. And so to show that two sets are unequal, I should be able to find something in one set that is not in the other set. And just notice from the definition of B that if some object X is in B, that implies that X is not a member of F of X. So I claim that for any X value coming from A, you can always find a difference between these two sets B and F of X. That there's going to be some object that's in one set that is not in the other. So the claim is that B is not equal to F of X for any X value coming from A. Now, if this is true, that B is not equal to F of X for any X value coming from A, then B can't be in the range of F, which means that F is not surjective, which proves the theorem. Now let's play around with this Cantor theorem construction, and let's see why that new set B isn't going to be in the range of F. So let's consider the set A. It's going to have 1, 2, and some function f, which I'm going to denote by these red arrows, mapping A to the power set of A. So I have 1, 2 here, and I'm going to map that stuff to the power set of A, which is going to have 4 members in it. It's going to have the empty set, or 0. It's going to have the set containing 1, the set containing 2, and the set containing 1, 2. And now consider the following mapping. I map 1 to the set containing 1, and I map 2 to the empty set. And now I observe f of 1 is going to be the set containing 1, and f of 2 is the empty set. And now let's construct that weird set B. Now to do that, I go through each x value in the set A, and I ask the question, is x contained in f of x? For example, is 1 contained in the set containing 1? And the answer to that is yes. So that means that 1 is not going to be in B. And then I go to 2. I ask the question, is 2 contained within f of 2? That is 2 contained in the empty set? The answer is no. That means that 2 is included within B. So I see here that the set B is going to be the set containing 2. Now notice B is indeed a subset of A, but now notice I have the set containing 2 here. There's no arrows going to it, which means that F is not surjective. So this is going to be that weird set that we construct, which is going to refute the idea that F is surjective. And I encourage you to play around with these arrows and power sets just to see that this construction is indeed going to produce something which is not in the range of F. Now it turns out that this proof of Cantor's theorem can be interpreted in a very nice way through a diagonal argument. That is, when I consider this mapping, for example, 1 going to the set containing 1 and 2 going to the empty set, that can create a table corresponding to this mapping. So what I'm going to do is I'm going to write 1 and 2 on the rows like this. So this first row is going to correspond to this 1, to x equals 1. Then the second row is going to correspond to x equals 2. And now the first column right here is going to correspond to f of 1, which I saw was the set containing 1. So I'm going to write that as the first column. Then the second column is going to be f of 2, which I saw was 0. Now what I'm going to do is in the interior of the table, I'm going to place zeros and ones by the following rule. The entry gets a 1 if the row value is contained within the column value. So this gets a 1 because 1 is contained within a set containing 1. This gets a 0 because 1 is not in the empty set. This gets a 0 here because 2 is not in the set 1. And this gets a 0 because 2 is not in the empty set. So I've created this table here, 1, 0, 0, 0, which represents the mapping here. And now notice that the entries on the diagonal here, the 1 and the 0, are recording the truth of the proposition is x a member of f of x. That is, this cell here is recording the truth of the proposition is 1 a member of f of 1. In this case, it's true, so it gets a 1. And this cell here is recording the truth of the proposition is 2 a member of f of 2, because 2 is here in this row, and f of 2 is in this column here. So the truth of the proposition is 2 in f of 2 is recorded in this cell. Now what do you do to construct that new set B is you examine the diagonal elements. And what you're going to do is negate them. So I come to the first diagonal element here. I notice it's a 1. So I create a new column vector by negating it to 0, or changing it to a 0. And then I notice here that the second diagonal element is a 0, so I changed that to a 1. So I created this new column vector 0, 1. And the way to convert this to the set B is whenever you see a 1, you stick that x value in the set. So notice here, I have 0, 1, so I have the 1 here. That means that I stick 2 in this new set B. So this is the way to construct B. And now notice that B can't be in the range of F, because the range of F consists only of the columns that I've constructed in this table. And this new column vector, which I'm going to call y star, can't possibly be any of these columns here, for the reason that the first element of that vector differs from the first column vector in the first entry, and it also differs from the second column vector in the second entry there. So that's why I negate those two diagonal entries. So this y star can't be found in any of the columns in this table, which means that this new construction, y star, is not in the range of F. And I encourage you to play around with this too, and sort of see how this sort of mechanically creates the new set B, which is not going to be in the range of F. Now I'd like to wrap up this video by talking about some of the properties of finite sets in terms of equinumerosity. So the first thing I'd like to talk about is the pigeonhole principle, which is it's a very intuitive idea, which says that no natural number is equinumerous to a proper subset of itself. So you have some natural number, let's say 4, which is a set containing 0, 1, 2, and 3. Take a proper subset of that, and there's no way that that proper subset is equinumerous. So hopefully that's pretty intuitive. And it's called the pigeonhole principle, in case you're wondering, because let's say you have 9 holes here, and you have 10 pigeons, and you're trying to stick 1 pigeon in each hole. So you go through each hole, doesn't matter what order you do it in, you put your first 9 pigeons in, and then you come to the 10th pigeon, and then you run out of space. So you've got to stick it in one of those holes. And the pigeonhole principle says that at least one of these compartments has 2 pigeons in it, at least 2 pigeons in it. This whole principle probably seems obvious, but it prevents bizarre statements like 2 is equinumerous to 4 or 10 is equinumerous to 5. So I'll leave the proof of the pigeonhole principle just as an exercise. And just to illustrate that in terms of the arrows, let's say I wanted to map 4 to 3. Remember, 3 is a proper subset of 4. So remember, to show that these two are equinumerous, I'm going to have to establish a bijective, that is an injective and a surjective function between the two. So let's try to construct such a mapping. So I map 0 to, let's say, 1. That was arbitrary. Then I've got to map 1 to either 0 or 2. I can't map it to 1 because that's already been used. So let's say I map 1 to 0. And then I'm forced to map 2 to 2 because that's the only thing that's left. So I've consumed all the pigeonholes here, and then I've got my pigeon over here, the number 3, and I can't map it to anything here, here, here. Otherwise, I lose the injective property. And what I'd also like to do is give you a definition for what a finite set is. I've been using that term finite, but I haven't given a definition. So a finite set is going to be a set that is equinumerous to a natural number. And just to sort of illustrate what that means, so let's say I have some finite set A, B, C, and D. And notice that I can put this into a bijective correspondence with the natural number 4, which is the set containing 0, 1, 2, and 3. And this is one example of a bijection that I can establish between those two sets. So that means that the set containing A, B, C, and D is a finite set. And the reason I introduced that definition next to the pigeonhole principle is because it follows from the pigeonhole principle that no finite set is equinumerous to a proper subset of itself. And notice that language, that no finite set is equinumerous to a proper subset of itself, is basically what I was saying for the pigeonhole principle. So this follows quite quickly from the pigeonhole principle. If you feel like proving it, then go right ahead. But it's a very quick proof if you're interested. And that'll wrap up this video. Hopefully you enjoyed this discussion on equinumerosity, which is going to very nicely lead into the topic of cardinal numbers, where we're going to start to talk about the different sizes of infinity. And as always, feel free to subscribe. Stay tuned for more videos on set theory. And if you enjoyed the video, give it a thumbs up. And thanks for watching.